Okay, so last class we did not get through our entire list. So I'm going to start by putting up some of those topics that were still on our list. But I want to open the floor again. If there's more topics that you guys want to add to it, things that you've thought about since Monday, let me hear them. Oh, actually, now I remember. We were going to talk about hybridization of some structures that we had up here, weren't we? Anybody remember the chemical formulas of what I had up there at the end of Monday's class? One of them was an iodine center, wasn't it? No. We had HClO, and we drew that as this. There was another one with yeah, the periodic acid. Yep. I think we had completely finished. What was our name for this one? What did we name it? Is it ionic, covalent, or more specifically an acid? This is one of our acids. So we know the name is going to end with acid. That's great. And it's either going to end with ic acid or us acid. And its name is, the root of its name comes from the root for the ion, ClO minus. This is not chloric acid. No. Chloric acid would come from chlorate, and chlorate is ClO3 1 minus. This is what? This is not chlorous acid either. Chlorous acid would be ClO2 1 minus. Hypochlorous acid. This is coming from the hypochlorite, so we call it hypochlorous acid. We were building the Lewis structures for these. I gave you guys this tip because this is not something that you will need to be able to predict on the unit test or on the exam. You won't have to predict that the hydrogen is bonded to oxygen. You just need to recognize that this is an acid, and I'm telling you now that as an acid, it's actually bonded to the O. But in building the Lewis structure, we said that we need to count the number of valence electrons, right? And that we had 1 from hydrogen, 7 from chlorine, and 6 from oxygen, and I did my math wrong last time. There's 14, but I said that we had 24. And we used up 4 of them right away by just drawing single bonds, because everything has to have at least a single bond. And the remaining 10 Typically, we put them first as lone pairs around outer atoms, and then as lone pairs around the central atom. 2, 4, 6, 8, 10. That satisfied the octet rule for everyone. So that's great. We're done. But I wanted to answer a couple more questions about hypochlorous acid. The central atom, oxygen, has what electron domain geometry? Raise of hands. Or electron geometry? Tetrahedral. Tell us how you got there.
There's
4 domains. 2 non-bonding domains, 2 bonding domains. And somebody else, it's molecular geometry. Quickly? Actually, I want to talk about what he brought up. He said linear. It looks linear. The H and the Cl are right across from each other. But I drew that just randomly. I could have put the H up here. I could have put the H down here. So I could have drawn the Lewis structure to look differently. We have to follow this breakdown of subsets of molecular geometries within electron domain geometry. The tetrahedral geometry, if one of those bonding domains becomes a non-bonding domain, it becomes trigonal pyramidal. If another bonding domain disappears and becomes a lone pair domain, we get a bent geometry. So the molecular geometry, the arrangement of the bonds relative to the central atom is bent. So actually, you nodded your head when I said linear, because they look straight across.
So wouldn't
The lone pairs do repel each other, and the lone pairs repel the bonding pairs as well. So the electron domain geometry, it has this shape where we use a wedge to represent something that's coming out of the plane towards you and a dash to represent something into the plane away from you. You can actually try to model the tetrahedral geometry with your fingers, but you kind of need 2 hands. So here is something in plane and then another bond in plane, and you can see there's a wedge coming towards you and a dash going away from you. Now take away one of those bonding domains and make it a lone pair. It's still repelling these other regions, but the arrangement of the bonds is now trigonal pyramidal. Take away any other of these bonding domains and make it a lone pair domain, it's still repelling all of the other groups. So you still have a tetrahedral electron geometry, but now the bonds are arranged just bent to each other. Not linear, which is hard to do with your fingers, but just bent. How many of you have made your cheat sheet for the midterm exam? Good. I actually can't offer this for this exam, but for the final exam, I'm considering, and I'd like to collect feedback over the next several weeks, I'm considering having you guys earn some points for submitting your revisions of the cheat sheet. So like submit your first version, you'd get some amount of points. Submit the second version, you get more points. Submit the third version, you get more points again. Why would I do that? To incentivize you to revise it. Not just to make it, but to build it and rebuild it and rebuild it again. How many of you, I guess there's only a few that have built it, did you put the geometry domains in there? Electron geometry and molecular geometry. Those can feel so challenging to memorize. So unless you're practicing and applying it and doing a lot of those problems, it might be worth just having a condensed version of it. Maybe you put abbreviations and you have a little corner of your sheet that has the table of electron geometries and the subset molecular geometries. Might not be a bad idea. Okay, Hybridization. Raise of hands, what's the hybridization of our oxygen atom in hypochlorous acid? So actually, we don't have to start with a number. That number that we put at the start is always the principal quantum number, the energy shell. And it is true that oxygen's valence orbitals are the 2s and the 2p's. But we don't have to typically put in whether it's 2s or 2p. Instead, you're going to see some combination of s with p. And there's only one s. And I don't know if I pointed this out, but s always hybridizes with some number of p's. You never get p's hybridizing without s. It's always s hybridizing with some number of p's. So we can start by saying sp, and then if it's just one p, we leave it. If it's 2 or 3, we have to say it. Ryan says sp3. Anybody agree? Yeah? Anybody want to back them up and explain why it's sp3 or how you can get there? Just count. 4 domains. S, P, P, P. It's as easy as that. But I will say the true reason is a tetrahedral central atom takes up 3-dimensional space. It doesn't take up space on a plane, and it doesn't take up space on a line. It takes up all 3 dimensions, which means that it needs the px, the py, and the pz orbitals, all 3 dimensions, to be hybridized. If I have a trigonal planar geometry, I only need 2 of those p orbitals. I only need px and py. The pz will actually be used in pi bonding, but the geometry is planar. And if I have a linear central atom, how many of those axes do I need? Just 1. I just need to be aligned along one axis, align. And that means sp. The other 2 p orbitals actually get used in pi bonding. Okay, so we have a true reason and we have a shortcut. sp3, which is exactly the same connection as how we got to tetrahedral, 4 electron domains. If it's tetrahedral, it's sp3. If it's trigonal planar, it's sp2. If it's linear, it's sp. Those always correlate directly. All right, let's count valence electrons for per iodic acid. Maybe we had started doing this at the end of last class, but let's do it again. Hydrogen brings how many? Sorry? Just 1. And how many hydrogens? Just 1. Iodine brings how many? And how many iodines? Good. 7 for iodine. Actually, I think I'm going to say that differently. I've got 1 iodine, and it brings 7. I've got 4 oxygens. Oxygen brings how many? Can somebody remind me how you can use your periodic table to find the number of valence electrons? Because oxygen is element 8, atomic number 8. How are you getting 6 electrons? Yeah, except for the transition metals and the inner transition metals. You can just look at that main group number that it's in. Oxygen is in group 6. That's its number of valence electrons. Another way that you can get there? Count within its row. Yeah, just start at its row and count over, skipping any of the transition metals or inner transition metals. So if you're in row 3, if you're in row 4 or lower, you count over and skip the D and F blocks. You're only counting S and P electrons, outermost electrons. Good. 4 times 6, 24. So 24 and 8, 32. You guys know you have a calculator on this, so you don't have to make silly mistakes like I did last time. You can always rest assured you've got this. What's the best way to start in building a Lewis structure? connect everything with a single bond. There may be double bonds in here, there may be triple bonds, but I know there will always be single bonds everywhere. That used up how many of my electrons? 10 of them. 2, 4, 6, 8, 10. That means I've got 22 left. What should I do with them? Yeah, let's start as lone pairs. It should be rare that you ever have to put a lone electron, a radical electron. So start by lone pairs. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. I used them all up. That's great. Let's talk about the octet rule. Have I satisfied octet rules everywhere? Okay. So I don't need to redraw my structure at all because I've got octet rules. That means that this is a valid resonance form. Is it the only valid resonance form for periodic acid? Talk to me about what I could change to make another valid resonance form. Actually, moving a hydrogen to a different oxygen isn't a resonance form. Resonance is the movement of electrons or the delocalization of electrons, the fact that electrons aren't necessarily here or there, but they're in both places. Can I make double bonds between the oxygens and the iodines? Which of the oxygens would I do? One of them in particular? All of them? A set? And why would I decide to make double bonds? When we're building Lewis structures, we say lone pairs should be moved into a bonding pair, meaning that atom doesn't lose them, but it starts to share them, only if that helps to satisfy the octet of another atom. But if we have octets, do I need to? What would be the only other reason that I would move electron pairs? Jacob. Formal charges. So let's talk about formal charge here. What is the formal charge on my central atom iodine? Who's got the equation for calculating formal charge? Which is that equation you need to memorize, by the way? No, actually. It's on your possibly useful equations sheet. So you can memorize it if you want to. It's pretty easy to remember once you do it enough. You can put it on your cheat sheet if you want to. You might have a whole section dedicated to molecular structure, or just recognize it's on your equations sheet, so you don't need to write it down again. Who's got it? What's my formal charge calculation equation? And there's different versions of it, right? Like the one that I give is different than the one that's on the cheat sheet, so whichever one works best for you is the one I want you to use. Alina? Good. Valence electrons. Minus dots. Plus what? Plus lines. Yep. Dots plus lines. I want to say the equations sheet might say it different, and it might say valence electrons minus non-bonding electrons minus half of the bonding electrons. Is that how it says it, Brian?
It says number of valence shell electrons in the free atom minus number of lone pair electrons minus half of bonding electrons.
Which, for those of you that love math, that's just distributing this negative sign into the parentheses. So the equation that you are given on the cheat sheet says, a bit of a paraphrase, valence electrons minus non-bonding electrons minus half of the bonding electrons. That's because you're subtracting both of these from the valence electrons, or you can just sum them and subtract them from the valence electrons. I am not forcing you to use a particular equation. I just find this one to be the easiest to get to from your valence structure. All right, so for iodine, what number goes here with valence electrons? We already said iodine was in group 7. It's one away from having an octet already in its valence shell. 7 valence electrons. How many dots surrounding iodine? 0. How many bonds surrounding iodine? 4. 7 minus 4 plus 3 formal charge. Again, a formal charge doesn't necessarily mean you have an ion, because this molecule is actually net neutral. That means if there's a plus 3 on one atom, there's a total of negative 3 somewhere else in the molecule. Where is that negative 3? Six dots and 1 line. So for these oxygens, the formal charge equation is 6 minus 6 plus 1. Each of these oxygens is a minus 1 formal charge. This one too? 6 minus 4 plus 2, 6 minus 6. So this one's neutral. It's got 2 bonds, 2 lone pairs. That's what oxygen likes. These are all negative 1, which is a negative 3 formal charge total, which balances my positive 3 formal charge total. Great. So there are multiple valid resonance forms of periodic acid. This is a valid resonance form. And any combination where oxygen shares double bonds or has single bonds is a valid resonance form. Here is the resonance form that minimizes formal charge. Can you prove that this has minimized formal charge? What's the formal charge on iodine now? 7 minus 1, 2, 3, 4, 5, 6, 7. 7 bonds. 0 formal charge. And the oxygens? 2 lone pairs, 2 bonds. So how many valid resonance forms exist here? Well, 1, 2, and then a ton of other combinations where this has 1 bond and these 2 are double, this has 1 bond and these 2 are double, this has 1 bond and these 2 are double, or these 2 are single and this is double, these 2 are single, etc. There's a lot of valid resonance forms because we go all the way from satisfying octets to completely minimizing formal charge. All of them are valid, but not all of them are equally contributing to the structure. Okay, what else do we want to talk about there? Hybridization of the iodine. Anybody disagree? 4 regions, sp3. Great. Let's talk about polarity. Which of the bonds in periodic acid is polar? I'll give you a list. We've got an I-O double bond, an I-O single bond, and an OH single bond. Talk to me about I-O double bond. Oh, this one's challenging, right? Because what do you need to know in order to determine polarity? Electronegativity. Well, as it turns out, the electronegativity of O to pretty much anything is polar. In fact, iodine actually has the exact same electronegativity as carbon. They both have an electronegativity of 2.5, I think. 2.5. The exercise health sciences are moving in from the LAC, and they've got a lot of heavy stuff that they're dropping off upstairs. Sorry about that. So I to O, polar or non-polar? Polar. Again, O to pretty much anything is polar. I to O double bond, polar or non-polar? It doesn't matter if it's a single or a double bond. Yikes, I'm actually scared for our lives. Always polar. IO single bond, polar. OH bond, again, O to pretty much anything, polar. Since this compound has polar bonds, it's a good candidate for being a polar molecule. It's possible that this is polar. But if a compound has all symmetric bonding, all of its bonds look the same, then the compound is usually non-polar. So what do you guys think about periodic acid? Is this a polar molecule, or is it a non-polar molecule? Talk to me, what do you think? If you want to talk about where the partial charges go, sure. Let's talk about that. Where is the partial negative and the partial positive on the IO bonds? Where's the partial negative? The more electronegative, so oxygen. And on the OH bond, where's the partial negative? Also on the oxygen. So if I was going to draw dipole arrows in this molecule, I could draw arrows here. Oh, I drew those the wrong way. Do you know why? Because it should always point at the more electronegative atom. And here. I don't know if that helps, right? Because again, we also have to consider molecular geometry when we're considering symmetry. But we have two central atoms. Iodine is a central atom. Oxygen of the OH is also a central atom. So talk to me about the iodine. Are all of the bonds going to iodine the same? There is a difference. The difference between IO double bonds and an IO single bond. Even if you look back at this resonance form, there's a difference. It's the difference between IO minus single bond and IOH single bond. Those are different groups. So there is a lack of symmetry surrounding that iodine. It's not all the same surrounding iodine. What about the oxygen atom? Does that have all the same type of bonds going around it? No. O to H, very different than O to I. Those are different bonds. We also said that if a central atom has lone pairs, it's a very good chance that it's a polar molecule. And this central atom does have lone pairs. So it both lacks symmetry in its bonds and it has lone pairs. Altogether, this says that this is a highly polar region of the molecule. This molecule is polar. If I were to draw iodine with its molecular geometry, here's that tetrahedral geometry. There's an O double bond going back, and then I've got this O single bond coming forward. You can see how this region of the molecule is quite different from this other region where all the double bonds are. And that's going to create a major dipole in this molecule that points towards this oxygen. This molecule lacks symmetry, and it has polar bonds. So this molecule is polar. Okay, what about hypochlorous acid? Polar or non-polar? Polar? Has polar bonds? Yeah, Cl to O and O to H are definitely polar bonds. Lacks symmetry and has lone pairs on the central atom. All of those contribute to being polar. Okay, let's talk about a couple of others in terms of the octet rule and polarity. I don't know if I actually, I know octet rule was one of the things we brought up last week, and I actually meant to bring it back here. I was able to break the octet rule with iodine, right? Why? Yeah. Good. Iodine has a d orbital in its valence shell. It doesn't necessarily try to fill its d shell, its d subshell, but the fact that it has d orbitals means that it can put extra electrons beyond 8 into those d orbitals. It's in row 3 and lower. Why didn't I violate the octet rule on chlorine? Why didn't I draw a Lewis structure where oxygen shares one of its lone pairs? Lone pair goes into a double bond. Can chlorine not violate the octet rule? It doesn't? So chlorine is not in row 3 or below? Actually, it is. Yeah, it is our row 3 halogen. So chlorine can violate the octet rule. So is this a good resonance form for me to suggest? Maybe. Technically, like, I'm violating the octet rule, but I'm allowed to violate the octet rule. Is there any reason I wouldn't want to violate the octet rule with hypochlorous acid, but I would want to violate the octet rule with periodic acid? Formal charges. Here, I violated the octet rule in order to minimize formal charge. Here, by violating the octet rule, I've actually created formal charge. That makes it not a valid resonance form. I'm only going to violate the octet rule if it means I can minimize formal charge. Formal charge is good if the octet rule is satisfied. Violating the octet rule to create formal charge, not great. Okay. So we said chlorine can violate the octet rule. It's not going to in this structure because we want to minimize formal charge. What about hydrogen? Is hydrogen obeying the octet rule? Yeah, hydrogen has 8 electrons around it. Hydrogen doesn't obey the octet rule. Why doesn't hydrogen obey the octet rule? What rule does it obey? It's not that it needs one. Hydrogen has one, but it needs 2. Hydrogen's nearest noble gas neighbor is helium, and helium has 2 electrons. Hydrogen being in the first shell can't obey the octet rule because it doesn't have space for 8 electrons. In the first shell, it only has space for 2 electrons. So hydrogen obeys the duet rule, which is why in these structures we don't see 8 electrons around hydrogen. We only see 2 electrons around hydrogen. And when you get into inorganic chemistry, so many of you are going to get there, you'll find a structure called diborane where hydrogen appears to violate the octet rule. It's very cool, but I'm not going to waste our time with it. I'm just going to make you think about that. Okay. Are we on the right track? Yeah, Alina? Hmm. Okay, so let me try to rephrase it, see if I missed anything. If we're given a question that says, which of these chemicals must violate its octet rule? Do you need to draw all of the structures? Yeah? So let's put some answers here. Let's say I've got carbon monoxide, I've got ammonia, I've got phosphorus trichloride, and I've got nitrogen dioxide. And the question is, actually, I'm sorry, I'm going to change nitrogen dioxide. And I want to say, let's say sulfur trioxide. No, not sulfur trioxide. Sorry. I'm trying to give us something that, I'm trying to get at something here. So the question is, which of these structures must violate the octet rule? Do I need to draw out the structures for every single one of them? What could I use to rule out some of these structures? Beautifully said. Carbon monoxide, only group 2 elements. Ammonia, only group 2 elements. Actually, group 1 and group 2. Carbon monoxide and ammonia cannot violate their octet rules. That's the reason I took NO2 off as well, because that was just another example where you couldn't violate the octet rule. So I don't even need to spend time drawing carbon monoxide or ammonia. Does that make sense? Rule out the ones that you can as quickly as you can, and then spend more time on the compounds that you're more concerned about. So which of these has a valid Lewis structure that must violate the octet rule? Do you guys have any guess? C must violate the octet rule? How can you be so confident? Because you know it? You've got to have 5 bonds to phosphorus. How many electrons in 5 bonds? Roughly 10 on average. Actually, that is a good point because there are things called 1 electron covalent bonds. There's also 2 electron 3 body systems, which is what I was talking about with borane. 3 atoms that share 2 electrons each. So you're actually right. On average, 5 bonds is 10. If you round up. You cannot draw 5 bonds to phosphorus without violating the octet rule. So maybe you don't even want to spend time sketching PCl5 because you know it's going to violate the octet rule. Maybe you want to also prove that there's a valid resonance form of SOCl2, thionyl chloride, that doesn't have to violate the octet rule. Now, we talked about drawing Lewis structures. The best idea is to quickly count all of your valence electrons, map them out, figure out how you're using them. At some point, you're drawing structures so frequently, this step might just be slowing you down. You might actually be able to get to a point where you can draw structures and then kind of guess the valence electrons that need to be in there, or do the counting later on rather than up front. So let's say we want to draw SOCl2. We're going to put S in the middle with oxygen on one side and chlorine on the other 2 sides. And we're going to connect them with single bonds. And we recognize that chlorine often likes to have just 1 bond and 3 lone pairs. And maybe we're not quite sure about oxygen. So this is where, if I'm not sure how many more electrons I'm going to have, and it's not apparently obvious, now I'm going to step back and say, I do actually need to count my valence electrons. One sulfur brings 6 electrons, one oxygen also brings 6 electrons, and 2 chlorines bring 7 electrons each, 26 electrons. I've actually used 8 right here, 16 right here. That's a nice number to subtract. That leaves me with 10. And I've used another 2 from this bond. So I've got 8 electrons left to put in. That's 2, 4, 6. Oxygen has an octet. 8. Sulfur has an octet. Every atom has an octet. I have not violated the octet rule. Is this a valid form of SOCl2? I know I went through that in kind of a weird way because I didn't start by counting the valence electrons. I came back at it to figure out how many more I should have. But is this a valid form? Do you have concerns about this form? What concern do you have? Okay, but with periodic acid, we also agreed this is a valid form, but it doesn't minimize formal charge. It's valid because there are octets, but there are other valid forms as well where we break octets and minimize formal charge. So, valid? Yes. The only form? No. There is another form of SOCl2. Chlorine keeps its single bonds. Sulfur keeps its lone pair. But oxygen takes one of its lone pairs and shares it with the sulfur. Brings oxygen from negative to neutral and sulfur from positive to neutral. So this is valid. This is valid. There is a structure of SOCl2 that doesn't violate the octet rule. And just so that you guys know what it looks like, this is what PCl5 has to start out as. No matter what I do, honestly, no matter whether phosphorus even gets more lone pairs put on it, octet rule is already violated. There is no structure of PCl5 that does not violate the octet rule. And I will say this, the unit test and the midterm, they both require a lot of questions, or they both have a lot of questions about structure. And sometimes you're not shown the structure. It gives you a list of molecules and says, find the answer about their structures. You don't have to draw all of them. You can rule out as many as you can up front and then lean into the ones that aren't as obvious. Okay, I think we still need to do a little bit more nomenclature, but otherwise we're pretty much there. Can I have you guys name these 3 compounds? Okay, Ryan gave me the first one. Actually, I gave it to you as well. And the second one has a common name. Its common name is ammonia, but that is not an IUPAC name. So let's review. When we're providing a name, we need to recognize first, is it covalent or ionic or an acid? Are any of these acids? I wouldn't be surprised if some of you were not sure about ammonia because there is an H there, and acids provide H's. But it's not one of the acids that you are asked to know. It's not a good acid at all. So they're not acids. Are any of these ionic? How can we recognize ionic compounds? Metal, non-metal. And remember that designator, it actually is a stair step along the main group on what's a metal and what's non-metal. But those metals are often very obvious. You know them as metals: lead, silver, copper, iron, tin, aluminum even. So I don't have any metals, but there is another way that you can have an ionic compound that has no metals in it. What about the compound ammonium nitrate? How many metals are in ammonium nitrate? 0. If you were given that, can you use that rule of thumb, metal and non-metal, to figure out that it's ionic? What do you need to use? You are right that an ionic bond has an electronegativity difference greater than 1.9. That's easy to tell if you just have like 2 types of elements, like FeCl3. Calculate the difference in that electronegativity. It's got to be an ionic bond. But here, the difference between N to H is polar covalent. The difference from N to O is polar covalent. And there is no bond between any of these elements with any of these elements. There is no covalent bond between them. What do you need to recognize about ammonium nitrate to know that it's ionic and not a covalent molecule? How do you know there are charges? What do you recognize about those combinations of elements? These are our polyatomic ions. You have to recognize ammonium, NH4, and you have to recognize nitrate. Those are not going to count as individual covalent compounds. They count as discrete ionic species. Cation, anion. And NH4 is 1 plus, NO3 is 1 minus. You have to be able to recognize that. Okay, so do we have polyatomic ions? I don't have any NH4 plus. I don't have any NO3 minus. I don't have any SO4 2 minus, SO3 2 minus, ClO minus, ClO2 minus, IO4 2 minus, right? Just non-metals, no covalent compound, no polyatomic ions, no metals. So the first one, I already named it. It's just 2 elements. You'll only ever be asked to name covalent compounds that are binary. You will not be asked to name covalent compounds that have more than 2 types of elements. And remember, our rules here is you can't predict how many of each atom will be present. These are not based on charges. So you can't figure out the quantities. You have to describe the quantities. 1 carbon would be monocarbon, but we never include the mono. If it's the first element, mono gets dropped. Carbon, monooxide, and then we do this weird thing where if you have doubling up of the same vowel, they often just get written as 1 vowel. So instead of monooxide, we write it as monoxide. Not monocarbon monoxide, just carbon monoxide. All right, you want to give me NH3? Anybody want to try? Not trioxide. It would be nitrogen trihydride, because we drop the suffix of the element and we replace it with IDE. But you'll actually notice oxide is an ion. Remember, oxide is 2 minus. So by saying carbon monoxide, I'm actually kind of implying the existence of an ionic oxygen. That's okay because oxygen is more electronegative than carbon. So there is partial negative in that molecule where the oxygen is. But what about hydrogen with nitrogen? Which one is more electronegative? Nitrogen is. Which means if there were ions in this compound, it wouldn't be hydride. It would be, what would we call nitrogen? Nitride. So we'll flip it. We're going to name the least electronegative atom first, the most electronegative atom last, changing the suffix of the most electronegative to IDE, because as the most electronegative, it would have that anion suffix. Do you want to try again? Name the hydrogens first and then the nitrogen. We have to name how many of the nitrogens. Just one nitrogen. So trihydrogen mononitride. Just like we had carbon monoxide to indicate there was one oxygen, we would call this trihydrogen mononitride. Carbon monoxide rolls right off the tongue because since before you were born, you have been raised about the dangers of carbon monoxide poisoning, which is scary, and it binds to the hemoglobin in your blood, and it suffocates your cells from the inside out. But I don't think you think about what carbon monoxide is communicating. It's communicating the quantities of the elements. So trihydrogen mononitride feels clumsy and awkward, but it's communicating the same thing. You guys remember the IUPAC name for water? Dihydrogen monoxide, H2O. Trihydrogen mononitride. All right. You know what? This actually means that we could name this compound. This compound has a chemical or a common name, which is hydrazine. Some of you engineering majors might know about hydrazine. It's explosive, but in organic chemistry, we use hydrazine in chemical reactions with organic molecules to reduce compounds. What would be the IUPAC name for hydrazine? Raise the hands. Good. Tetrahydrogen dinitride. It's still binary, right? It's still just those two elements, nitrogen and hydrogen. So it's a valid compound for you to name. It just means finding the most electronegative and naming it last, changing its suffix. I actually mentioned this, I think, when we learned about nomenclature in like Unit 2. You have to kind of memorize some of those chemicals without understanding why you place the names where you do. And I mentioned we name them based on electronegativity, but that's not clear up front because we didn't learn about electronegativity until Unit 4. All right, who wants to give me PCl5? I'll give you a hint. This compound, you don't have to figure out which one is more electronegative, although your periodic table would be it would be easy to figure out from the periodic table, but this one is written as you would expect. It is not phosphorus hectachloride. Hecta, I think, is 100. Hecta. Anybody? What's 5? Penta. You're maybe thinking of hexa or hepta, which is 6 and 7, but hecta is 100. Like if you have a hecta, a hectare of land is 100 acres.
So just rock with the shapes and how many sides they have and just take the prefix of those?
Yes, rock with the shapes. Why didn't you call it monophosphorus pentachloride?
Because you drop it if it's first.
We can drop mono only for the first element. Phosphorus pentachloride. Now you guys are kind of lucky. You know that all of your questions are multiple choice because that means you can't get marked off for spelling errors. When I was in high school, if we spelt phosphorus wrong, our teacher would just like, no points for that name. You know, same for fluoride, which is always, it's spelt a little bit different than people expect. But you guys don't have to think about the weird way that phosphorus is spelt. Anyways. Which of these do you think we should lean into more? Any new topics you guys want to come up with? I need to clear the board of some of these old examples. Any old topics we covered Monday that you want to come back to? We've got an hour. And by the way, if you want to get up and move around, now is a great time to do it. But I'm going to give you guys this full hour for working on things. How many of you finished your unit test? Oh, that's like the same number of hands. Oh, that's more hands. That's great. The unit test. How many of you got your midterm rescheduled? Great. I was worried about that. And here I am telling you guys, schedule them early. Find a spot. Yeah, just wait for the testing center to flood and cancel all of your hard work. Oh, and now I actually have resources again, so we can look at worksheets, we can look at active, we can look at practice unit tests. That would be a good one for us to go through. Should we go through this together? First one, easy, hard? Raise of hands. What is the chemical formula? You guys have answered too many times. Is that a hand?
I know two.
Okay. You guys agree? Great. Much harder. No? We should start by counting what? Valence electrons. One nitrogen brings how many? 5. 2 oxygens bring how many each? 6. 12 total. Ooh, look at that number. Nice. When you see an odd number of electrons, can you have electron pairs completely? No. And that happens with nitrogen more often than not because nitrogen brings an odd number of electrons with it. So unless it's paired with something that also brings an odd number, it can be really challenging. All right. What atom should go in the center? Nitrogen goes in the center. O is on either side. Single bond them once. I've got 13 electrons to put in. 2, 4, 6, 8, 10, 12, 13. Again, try to pair things when you can, and only put a radical when you can't. Nitrogen is usually that radical species. Is this a good Lewis structure? It's not good because I could get closer to an octet on nitrogen. Right now, nitrogen only has 5 electrons around it, 2, 4, 5. It wants to have 8. It's never actually going to get to 8 here, but it could get closer than 5. What could I do? Yeah, take one of these lone pairs from either oxygen and keep it with oxygen, but use it as a bonding pair. Now I'm at 7 electrons, which is as close to an octet as nitrogen is going to get. Is this the only valid resonance form for nitrogen dioxide? How many total valid resonance forms exist? 2. Could have gone with the double bond with either oxygen. Any formal charges in this structure? Where are they? Yeah, we know that oxygen with a single bond, that's a common bonding pattern. That's got a negative charge. But is this compound a negatively charged compound? No. There must be a +1. And it can't be on this oxygen because that oxygen is bonded how it likes to be bonded. So just a quick count, 5 minus 1, 2, 3, 4. That positive charge is on the end. Can I avoid that at all? No. I'd have to double bond from that other O, and that would violate the octet roulette N. So I'm not able to minimize this formal charge at all. Okay, so how many non-bonding electrons on the central atom? Just 1, which is a strange number. I was going to say an odd number, quite literally. It's a strange number because oftentimes your central atom has 2 non-bonding electrons, 4 non-bonding electrons, 6 non-bonding electrons, but this has 1 non-bonding electron. Okay, what is its molecular geometry? Raise of hands. Berkeley? You don't feel too confident. Ryan, you want to back her up?
I think it's bent or angular.
Oh, angular. That's an interesting one. I don't think,
No,
you won't see angular come up on the exam. If you see it on a table,
it just was
interesting. I've never actually heard that one before.
said that on real terms.
Oh, huh. That's a weird name, don't you think? Because like they all have angles. Okay, angular. Yeah, but I don't think you'll see angular on the unit test or exam. Anybody want to confirm with Berkeley and Ryan that this is a bent geometry? How can you support it? Do you want to try and support it? There's not 3 bonding regions. There are 3 electron regions, 3 electron domains. Those 3 are going to repel each other. What's the electron geometry of nitrogen dioxide? Trigonal planar. 3 regions, those are going to spread out onto a plane. and they're going to spread out as far as they can. That'll take the shape of a triangle, trigonal planar. And one of those regions is non-bonding, so the other two regions look bent relative to the central atom. So electron geometry, trigonal planar, molecular geometry, bent. Anybody else want to answer whether this compound is polar or non-polar? And here's the deal, if you don't feel confident, even better. Shout it out, and maybe we can try to figure out what we can identify, what you're struggling with, to identify whether it's polar or non-polar. Alina? Mm. It looks like I could split it symmetrically here, right? And we even discussed how either of those oxygens could have the double bond, which means that actually both oxygens have a bond and a half. But that's not actually its geometry. Its geometry looks more like this. And it still looks like I could split it here, but this wasn't the only symmetry that I could find here. I could have also found symmetry here where it's all perfectly in line and I could just split each atom in half. But can I find that same symmetry now? On the bottom half, I have both of my oxygens, and on the top half, I have none of my oxygens. I still have that kind of symmetry here, but I lack that symmetry here. So I gave you guys a tip about what to identify in a Lewis structure that gives a hint that it's polar. What does this use about that tip? Central atom has a lone pair on it, or I guess in this case, a non-bonding region. And that's going to create some asymmetry in the molecule. I'll have regions that are bonding and regions that are non-bonding, and those regions won't be able to reflect into each other. So Alina, you said you feel like it's polar despite it having the same type of bond. Do you feel validated now? Polar molecule. I want to take actually a side look. If you were given the molecular structure of ozone, you actually get a very similar structure. Has a positive charge on the central atom, a negative charge on one of the side oxygens. So that central atom has a double bond and a single bond, which could have been drawn on either side, and it has a non-bonding region. Polar or non-polar? There is a difference between NO2 and O3. What do you think it is? But actually, my tips of having lack of symmetry, having different types of bonds, having lone pairs on the central atom, that had one big caveat at the start. Right. You cannot have a polar molecule that doesn't have a polar bond. So we actually jumped over the assumption that N to O is polar. And it is. It has an electronegativity difference of 0.5, I think. I think it's 2.5 to 3.0 nitrogen to oxygen. Might be larger than that. So N to O is polar, which means this molecule has the capacity to be polar, but it doesn't necessarily have to be polar if there was symmetry all around. Like, here's a weird example, but the nitrate molecule, is a net 1 minus, has 3 formal charges, 2 of them cancel each other out. And it has 3 resonance forms. The double bond could be at any of those positions. Nitrate is also a trigonal planar geometry, although it's also trigonal planar molecular geometry. Is nitrate polar? Is the nitrate ion a polar molecule? No. It's an ion, so it has a formal charge always. It has a discrepancy between protons and electrons, but it's not polar. It doesn't have one region that is more positive and one region that is more negative. It is equally charged all the way around. Isn't that odd? That ions are actually not polar often, or always. Some ions are. That's nitrate, NO3 minus. But this is nitrite. Oh, actually, this is no longer. This is nitrite, NO2 minus. Is nitrite polar? Yes. So some ions are also polar compounds, and some ions are not polar compounds. Being ionic and being polar are not mutually exclusive, and they're not mutually assured either. It totally depends on the compound. Ozone, polar or non-polar? Non-polar. So the reason I brought that up is because, yeah, we follow the same rules. Ozone lacks symmetry in the same way, but an O to O bond is pure. There is no difference in electronegativity. I can't have one atom that is more positive and one atom that is more negative. Despite the fact that there are actually formal charges, there are no partial charges. And again, this is just a bad representation of the molecule. A better representation of the molecule looks like this. A double bond split between both of the oxygens on either side. Does that feel like a better representation? I don't know. That's for you to decide. Okay. Good review of polarity. Yeah, good application. Percent composition. What is the percent composition of nitrogen in nitrogen dioxide? Anybody want to tell me how I can set up this equation? Good. Good. Molar mass of nitrogen divided by the molar mass of NO2. So let's calculate the molar mass of the compound, or we can plug it in into the equation, whichever works best for you guys. Molar mass of the compound would be the mass of nitrogen. What's that? From our periodic table. Yeah, I'm going to round it to 14 grams per mole, plus the molar mass of oxygen, which is 16 rounded up grams per mole, times 2. So that means the molar mass of NO2 is 32 plus 14, 46 grams per mole. Per how many moles? Per 1 mole. That's the definition. So this equation then, we get 14 grams per mole divided by 46 grams per mole. I forgot a piece of this, didn't I? Times 100. Because percent is just like parts per 100 or parts per million or parts per billion. We got to multiply by that percentage. Calculator exercise. Let's round it to 3 sig figs. What do you get? Any units with this percent composition? Grams per mole cancels with grams per mole. This should be a ratio. It should be a percentage. It shouldn't have any units with it. But it is 30.4% nitrogen. So if you wanted to add any unit, it would be the fact that it's percent nitrogen. All right. What? Yeah.
At the beginning of the equation, you have
Molar mass N.
N, and then on the bottom, is it just O2?
Molar mass NO2. Because we're looking at the percent nitrogen in the whole of the compound, NO2.
Oh, so you're taking what you got on the bottom there, and you're plugging it in.
Yeah, this is 14 plus 16 plus 16, which is 46.
Okay.
Yep.
Thank you.
All right, here's another calculator exercise for us. How many atoms, unspecific, how many atoms total in 2 times 10 to the 27 molecules of nitrogen dioxide? If we were on our roadmap, this is a roadmap problem. Yeah. We're going to start on one side, molecules or things, particles of NO2, and we want to get to the other side, particles of atoms, which means I have to convert through a mole-to-mole ratio. There's no way to convert particles of one thing into particles of another without going through a mole-to-mole ratio. So this is where having the roadmap on your cheat sheet is very helpful because it reminds you what conversions you'll need to do. What conversion will I need to go from molecules of NO2 into moles of NO2? I need Avogadro's number. And then what about moles of NO2 into moles of atoms? I'd need the mole ratio, mole to moles, which really just comes from the chemical formula and extracting whatever information you need. And then lastly, I want to get to, I can't say molecules of atoms, but number of atoms, total atoms, which is going to use what? Molar mass cancels with moles and leaves me with grams. Am I looking for mass? I need Avogadro's number here. Again, because I'm trying to find total number of atoms, not trying to find a mass at all. I'm going to solve this one out step by step. If I had 2 times 10 to the 27 molecules of NO2, I'm going to cancel molecules of NO2 and come into moles of NO2. So I'm going to put molecules on the bottom, moles on the top. 1 mole of NO2 is 6.022 times 10 to the 23rd. Is that number on your equations sheet? I forget. I'm glad you have it printed. Not on your equations sheet. So this is something we have to know. You've got to have it on your sheet, your cheat sheet, or you've got to know it. This looks like a job for a calculator exercise. And remember, at this point, you should know how to use your calculator, whether you need to be putting parentheses in or whether you don't. If you're still struggling with that, please talk with me and we'll work through it. All right, for this, I get 3.321 times 10 to the 4th moles of NO2. 3,000 moles. You know, we could figure out how much that actually weighs because we have the molar mass. That would be multiplied by a molar mass of 46. This weighs 152 kilograms. You know how much 152 kilograms weighs? This table is way more than 152 kilograms. So 152 kilograms is something you could carry, maybe not easily. No? No, that's like 2 people. Depends on how strong you are. Maybe this is 152 kilograms. It's a little heavy. I think it's like 2 people. Yeah, a person is like 70-ish kilograms. So 152. 160 pounds.
360.
Okay, a big guy. Yeah, you could carry that. Okay, you could put it on a wagon and you could wheel it out of here. It's what they dropped off upstairs, man. It's actually like a measurable amount. 152 kilograms is something that you would experience day to day. You find things that weigh 152 kilograms. It's not a weird number. Okay, here's the reason I picked this. I saw a YouTube video today that said dropping 2 times 10 to the 27 balls at once, and then it showed like what in an ellipse, and it showed like how they move based on how they bounce. I was curious how many moles that was. I didn't have time to do the calculation. It's 3,000 moles. Okay, anyways, if that's how many moles of my molecules I have, moles of NO2 multiplied by, I want to cancel moles of NO2, and I want to get into moles of atoms. How many atoms in a molecule of NO2? How many atoms in a molecule of NO2? One nitrogen, 2 oxygens, 3 atoms. That's why it's unspecific. It's not atoms of N, it's not atoms of O. We're just looking at total atoms. In 1 mole of NO2, I have 3 moles of individual atoms. Remember, this is kind of like the bread analogy. If I've got 1 mole of bread, I've got 2 moles worth of, if I've got 1 mole of sandwiches, I've got 2 moles worth of bread, because each mole of sandwich has 2 pieces of bread. So I'm just going to triple this number. That number times 3. Do you know what? It was not. Yeah, it was. Never mind. It was 152 kilograms. I convinced myself it wasn't.
So it should be 3.3
You're right. It should be times 10 to the 3rd. Thank you. Not times 10 to the 4th. Which actually didn't affect me much because I didn't rewrite it. I just used the calculation in my calculator. But that was a good catch. That changes things here as well. That's how many moles of atoms we have. What's my last conversion? In 1 mole of atoms, I have 6.022 times 10 to the 23rd total atoms. This feels funky because I like, what am I going to say, particles of atoms or things of atoms? It feels like I'm missing another unit, but atoms is kind of already its own unit. So take that answer we got, 6.022 times 10 to the 23rd. I don't know about you guys, but I got an exact even number. Okay, that's nice. 6 times 10 to the 27th molecules. Nope, not molecules. Atoms. Does that number surprise you at all, Berkeley? Correct. But also, because the mole ratio was a simple 3 to 1, no, but actually you're right. We multiply by Avogadros, we divide by Avogadros at some point. So those numbers do just cancel each other out. Absolutely. We ended up just multiplying 2 by 3. In fact, that same thing can happen if you go from grams of something to grams of something else. For instance, there are chemicals that weigh like 44 grams per mole, and in a chemical reaction, they can make another chemical that weighs also 44 grams per mole. So if you're looking at how many grams of A will make how many grams of B, and they've got like a similar, just an easy mole ratio, you need their molar masses to convert to mole ratios, but then their molar masses just cancel each other out. You're right. I guess I've never done a problem. I didn't realize they were going to cancel. But now you know. So you can save yourself the work if that comes up on the midterm. Okay, I pulled up a worksheet on concentration, and it gave me a chemical that we should talk about. Because it's a chemical I'm not sure I covered well in lecture ever. And it's necessary for calculating its molar mass. The question was, what is the concentration what is the molarity of 43.8 grams of copper to sulfate hexahydrate. It's pentahydrate. Dissolved in enough water to make a 125 milliliter sample. You know what? I've got some of the numbers wrong, but it doesn't really matter. Numbers are numbers. We'll make this work. It's not like the final answer was a nice number either. Okay, actually looking at it now, it gave both the chemical formula and the IUPAC name, but I want to work with this IUPAC name. Do you guys remember naming these types of complexes? Do you remember it from Unit 2? No? It's really not challenging, but salts like copper sulfate, they pull in water quite easily. They've got these partial charges on their on water that are attracted to the charges of the ions. So when you purchase a chemical like copper sulfate, you're usually purchasing some hydrated salt. Sometimes it's 2.5 molecules of water per molecule of copper 2 sulfate. In this case, it's 5 molecules of water per molecule of copper 2 sulfate. So we could write this chemical formula, copper 2 sulfate pentahydrate. I feel confident that you guys could get this. Anybody want to give me the chemical formula of the copper 2 sulfate? And maybe don't just give it to me, work it out. How do you get the chemical formula of copper 2 sulfate? Did you say CuS? Oh, it's not copper 2 sulfide. If this was S alone, 2 minus, you're right, but that would be IDE. Sulfate is one of our polyatomic ions. Not to be confused with sulfite. This is sulfate. SO4, 2 minus. What is sulfite? It's not SO3 minus. It's SO3 2 minus. It has the same charge. All of those families, nitrate, nitrite, -1. Hypochlorite, chlorite, chlorate, perchlorate, all 1 minus. Phosphate, 3 minus. I don't know that there is a phosphite that's common. Sulfate, sulfite, both 2 minus. So this is what we're dealing with. And copper, how do you know it's 2 plus? Given to you right in the IUPAC name. By the way, how many metals tell you in the name their ionic charge? Like a dozen maybe? Iron, copper, chromium, vanadium, titanium, vanadium, titanium. That was a list that I sent you guys in one of our early announcements. That's something you should know, because I want to say even on the Unit 1 to 2 test, there was a question that said, what's the appropriate way to name this silver compound? And it gave you like silver nitrate or silver 1 nitrate, but there is only ever silver 1. So you don't call it silver 1, you just call it silver. And so putting the Roman numeral in when it's not required is wrong. Similar to, yeah, I erased it. Similar to putting in monocarbon monoxide is wrong. We always drop the mono from the first compound. All right, so what's the chemical formula of copper 2 sulfate? And I just want to reiterate this again to make it clear. A lot of students, when they're learning this for the first time, they think the 2, verbally, it sounds like they're saying 2 sulfates. How many sulfates in this chemical formula? 1. Because that 2 is talking about the charge on copper. All right, the way that we write the chemical formula when it's a hydrated salt is we actually put this dot. It's copper 2 sulfate with how many equivalences of water? That's what hydrate is getting at. You raise your hand for it? 5. Pentahydrate. You guys can see how hydrate is telling us that it's water. Would you have named it something differently? Would you call it penta dihydrogen monoxide? Pentahydrate makes sense, right? Hydrate or dihydrate. Why is it important that we know that there are 5 equivalences of water per 1 equivalence of copper sulfate? If you're dishing this out of a reagent bottle, that changes the molecular mass. It's not just copper sulfate that you're pulling out. You're also weighing physical water. And we need to know the molar mass of copper 2 sulfate pentahydrate if we're going to convert grams into moles so that we can get molarity, which is moles over liters. So why don't you use your periodic tables and calculate the molar mass of copper 2 sulfate pentahydrate. There are a lot of right ways to calculate this. The way that works right in my brain is to get the mass of copper, the mass of sulfur, the mass of the 4 oxygens, and then the mass of the 5 waters. Because getting the molar mass of water is really easy. And to break it down to say, I've got 5, or really 10 hydrogens, and then 5 oxygens, it's a lot more work than just saying 5 equivalences of water. And if I already know that oxygen is 16, water is a quick and easy 18. What did you guys get? $250.5? $250.5? I got 249.5. Okay. Anybody disagree? Anybody get the same? 249.5 grams per mole of copper sulfate hexahydrate, pentahydrate. Okay, I didn't copy this exactly the way it was written on this worksheet. The way it was written was, what is the molarity of copper 2 sulfate, not the molarity of copper 2 sulfate pentahydrate. So we can convert 43.8 grams of copper 2 sulfate hexahydrate, grams copper 2 sulfate pentahydrate, into moles of copper 2 sulfate hexahydrate using this molar mass. 1 mole is 249.5 grams. But that's not moles of copper 2 sulfate. That's moles of copper 2 sulfate pentahydrate. Which means technically I have to do a mole to mole ratio. Once I find out how many moles of my hydrated salt I have, I'd have to find out how many moles of the dehydrated salt I have. Let's do this conversion first. 43.8 divided by 249.5. Tell me what you guys get. You say 176? 176? Okay. 0.176. That's if you want to round at the third decimal place. We've got 3 significant figures here. If you don't want to round yet, what'd you get? 5.555 moles of copper sulfate, copper 2 sulfate, pentahydrate. Now I have to do a mole to mole ratio? Seriously? What would the mole to mole ratio be? How many moles of CuSO4 in CuSO4 5H2O? 1 to 1. Okay, I'm not going to waste my time on the exam writing this out on my scratch paper. But I am going to think about it, and I'm going to prove that that's right. 1 mole of copper 2 sulfate per 1 mole of copper 2 sulfate pentahydrate. It would be different if I was looking for the number of moles of water. It'd be 5 times this number. But the moles of copper 2 sulfate is just 1 to 1. So is that my molarity? What do I need to do? I need to divide by liters. And do I have liters? It depends on how quickly you can do this type of conversion. You could set up another conversion to say 125 milliliters. 1 liter is 1,000 milliliters, so I divide by 1,000. Or maybe you're getting quicker with converting milliliters into liters, and you can just say, I'm going to go from small unit to big unit. So I'm going to go from big number to small number. I'm going to take my big number, and I'm going to move the decimal place to the left 3 times. I'm going to divide by 1,000. Divided by 0.125 liters. But let me show you that conversion again in case it's useful for you. (125 milliliters), 1,000 milliliters to 1 liter. Big unit, small number. Small unit, big number. Just divide by 1,000. Question, will my molarity be a number larger than 0.175, equal to 0.175, or smaller than 0.175? Larger. When I divide by a number less than 1, the number on top gets larger. I love just mentally checking that my calculated answer agrees with my expected answer. I expect that this will be a larger number at the end. That scared me. What do you guys get? And we'll round to 3 sig figs, yeah? 1.40 molar. Moles per liter. That's our time, guys. Thanks for coming. Good luck on your midterm. This is the weird part. Monday morning, right into Unit 6. No breaks. We're going fast. I know a lot of you will not have taken the midterm exam by Monday. I know that I extended the midterm to go all the way through next Wednesday so that you guys can find time to fit it in your schedule. But that doesn't mean I'm wasting any more time on it. We're moving on. So do what you need to do to both come prepared Monday for Unit 6 and keep preparing for your midterm. All right? Have a good weekend. Take care, guys.